Hi, my name is Anthony, and I will be presenting our study entitled An Exploratory Study on the Occurrence of Self-Admitted Technical Debt in Android Apps. In this study, we conduct a large-scale empirical study that explores the occurrence and characteristics of self-admitted technical debt in over 15,000 open-source Android apps. Nowadays, building mobile apps is very easy. IDEs, frameworks, and libraries provide almost anyone with the ability to create sophisticated apps quickly. However, mobile apps are software systems and are also subject to quality issues, including poor code quality. While some instances of poor code quality might be unintentional, some code issues might be intentional. This is known as technical debt, where developers knowingly compromise the code and design quality in favor of meeting project deadlines and milestones. Moving on, there are instances of developers consciously acknowledging the presence of technical debt in their system through documentation, typically taking the form of comments, and these are known as self-admitted technical debt, or SATD. Now, SATD provides a convenient mechanism to study some of the suboptimal decisions that developers make when implementing a system. Prior work has mostly focused on SATD occurring in traditional non-mobile systems, such as the extent to which they exist and the rate of removal. However, there is a lack of research on its occurrence in mobile systems, especially Android apps. It is important to study technical debt in mobile apps as these apps have unique characteristics, such as reliance on user interactivity, supporting multiple types of devices, and so on. For example, in this code snippet, the developer has to implement workarounds in their code to support different mobile devices. More specifically, to turn off the camera flash for Samsung Galaxy and Samsung Behold 2. These are two different types of phones. This complex scenario is something that app developers face in order to support end users, and hence this is something that's less common with desktop and web applications. While there are numerous studies on SATD, most studies are focused on non-mobile systems. Of the few studies focusing on mobile apps, these studies have used code smells and other metrics to analyze technical debt in apps. Additionally, the research community has also produced refactoring-related tools. These include tools that use the feature flag and tools that depend on SonarQube. Therefore, the goal of this study is to improve our understanding of SATD in mobile apps. We are interested in discovering the extent to which SATD occurs in apps and the types and causes of these suboptimal implementations. We envision our work helping developers with better understanding parts of their code that is prone to technical debt, and also help the research and vendor communities with building tools to help developers with maintaining their apps. To this extent, we propose three research questions. The first research question: to what extent do open source Android app developers document technical debt in code? The first research question is quantitative, where we want to understand the volume of SATD typically contained in Android apps. RQ2: what are the specific types of self-admitted technical debt occurring in open source Android apps? In the second RQ, we are interested in knowing the category that these instances of SATD fall under. These are predefined categories that have been proposed in prior literature. Finally, in the third RQ, we are interested in understanding the mobile and Android specific elements that are typically involved in technical debt by examining the keywords in the SATD comments. This study provides preliminary yet promising findings that expand our awareness of technical debt in Android apps. Through our findings and discussion, the community is made aware of the similarities and differences of technical debt in mobile and non-mobile systems, along with the typical elements in an app that are prone to suboptimal implementations. Shown here is an overview of our methodology. We utilized an existing dataset of Android apps known as Android Zoo Open. We successfully cloned over 37,000 apps that were listed in this dataset. These apps use GitHub for version control. Next, we built a custom tool that utilizes Java parser library to parse each source file. Through an AST, we detect all comments in a source file and then use an existing SATD detection tool to determine if a comment is an SATD comment. We extract all SATD comments. The detection tool is known as SATD Detection Core and has been used in prior studies. The tool utilizes NLP techniques and binary machine learning model to classify the comments. Additionally, we also use a tool to count the number of lines of code in the source file. All this extracted data is then used to answer our research questions through quantitative and qualitative techniques. Some numbers from our dataset include over 1 million Java files analyzed, with each project having a median of 10 Java files, and over 14 million comments that were analyzed. Next, let's look at the findings from our experiments. In RQ1, we want to know the extent to which SATD occurs in Android apps. We detected over 450,000 SATD related comments, with an app having a median of 4 SATD comments and a median of 2 SATD files. Looking at the SATD comments in a file, each SATD file has a median of 1 SATD comment. SATD related comments contribute to, on average, around 5.97% of an app's comments. We also observe that files with SATD have a significantly higher median number of lines of code than files without SATD. Running a Spearman correlation test shows a moderate to positive correlation between the number of Java source files and SATD comments in an app. In summary, RQ1 shows that Android app developers do make suboptimal decisions when building their apps. However, the volume of SATD comments occurring in mobile apps is far less than those that occur in non-mobile systems. Let's move on to RQ2. So RQ1 shows the existence of SATD in Android apps. Next, we categorize the SATD comments into 7 predefined categories. These categories are code, design, requirement, defect, documentation, test, and unclassifiable. These categories have been defined and used in prior literature. We manually reviewed a statistically significant sample of comments to perform this grouping. In total, we reviewed 386 SATD comments. This equates to around 95% confidence level and a 5% confidence interval. We observe that code debt is the frequently occurring type of SATD comments in apps. This is similar to non-mobile systems. Code debt comments include workarounds developers have implemented to fix a bug, the need for identifier renaming, data type changes, placeholders for missing code, and so on. Moving on, under design debt, we see developers documenting shortcomings in the app structure. These comments include the need to refactor code, such as moving code from one location to another and the application of object-oriented principles. The requirements category include comments showing the need for documenting missing or incomplete functionality. We also observe developers highlighting the need to support other versions of the Android operating system. Defect comments are documentation of known deficiencies and the need for a fix. Documentation comments are reminders to document the behavior of the code. Test refers to the need to create or run tests. And finally, any SATD comment that did not fit into any of the above categories were marked as unclassifiable, such as the example shown here, which is to do, it's bad. Our paper provides more examples from the dataset for each category. So please do refer our paper to learn more about these categories. Finally, in RQ3, we examine mobile and Android-specific elements that are prone to technical debt by analyzing the words in SATD-related comments. More specifically, we utilize NLP techniques to extract frequently occurring n-grams. We then manually examine the top 50 unigrams, bigrams, and trigrams and group them into related categories. Our analysis yields 4 high-level categories. Furthermore, some of these categories are composed of subcategories. The 4 main categories are Android SDK API, General UI, General Programming, and Hardware. The Android SDK API involves suboptimal code related to developers using the Android SDK to build apps. This also includes UI components such as activities and fragments. Hence, we observe terms such as activity, view, fragments associated with SATD comments. These terms are related to the presentation layer. The general UI category involves comments related to implementing new or missing functionality related to the app's user interface, such as color, positions, buttons, and so on. Moving on, the general programming category includes terms related to general programming concepts or activities, where developers document the need to improve code via refactoring or improve error handling, storage, security, and so on. Under hardware are SATD comments describing code workarounds for integrating with specific devices such as cameras. Again, our paper provides more examples from the dataset for each category, so please do refer our paper to learn more about these categories. Moving on, we summarize the findings from our 3 research questions. Similar to non-mobile systems, mobile app developers also make suboptimal decisions when implementing their apps. However, the volume of SATD comments in mobile apps are lower than non-mobile systems. This can be due to mobile apps being more constrained in functionality and therefore size. Our observation of mobile apps being more prone to code debt aligns with prior work on non-mobile systems. Likewise, our observation of developers documenting shortcomings with Android UI specific features also align with prior work on presentation layer code smells. Furthermore, security-related SATD comments are aligned with prior studies that investigated Android permissions and data leakage. Based on our findings, we propose the following takeaways. The first takeaway involves educating developers about the importance of integrating tech debt-related tools, such as those proposed by the research community, into the development workflow, such as integrating it into the build process. The second takeaway is around expanding research into mobile technical debt. As an exploratory study, our findings identifies Android-specific elements that are prone to suboptimal issues. This opens the door for future work that looks more deeply into Android-specific features. Furthermore, there is also an opportunity to conduct similar studies on iOS apps. The third takeaway is about the opportunity to build tools and techniques to detect mobile-specific technical debt. And the final takeaway is to complement tool usage with code reviews. The review process can catch instances of poorly composed SATD comments such as vague or incomplete comments. Finally, in conclusion, Our study examines the occurrence of SATD in mobile apps. Through a large-scale empirical study, we show that mobile apps are subject to poor programming practices, where developers document the workarounds or shortcomings in their code. We manually reviewed a statistically significant sample of SATD comments and grouped them into related categories based on their debt type. Likewise, we also identified mobile and Android-specific elements that are prone to suboptimal implementation. Finally, our future work involves examining the repayment and survival of SATD in Android apps by analyzing the version history of source files. And with that, I've come to the end of my presentation. Thank you.